Hey, what's up, guys? Okay, so today I want to talk about the Fourier transformation of Boolean function. This is interesting topic, and I recently learned about this, and I think this is more computer science perspective. So I will put so this is more computer science topic. So I will put in the separate list in my theoretical computer science. And I hope you guys subscribe to my channel. So today I will introduce the basic notation and the basic idea of the Fourier transformation of Boolean function. Whew. Okay, so it based on what kind of Fourier transformation that your background is. So if you're like the engineering or the physics is, or you learn some basic, if you learn the real analysis, then your usually Fourier transformation is continuous. So idea is that somebody give you a function that R to be, or basically can be R to be the non-real number, and somebody say this f is a time domain, right? So you can times this exponential minus I omega t and then do dt, and you do this transformation, and you call this f has omega. So f omega will be say in the frequency domain. This is somehow like the terminology, so it's not important. You can change this to be x and y. Okay, so one is that you can just change this to this. Okay, now this is the Fourier transformation. Okay, and in your higher mathematics, that you can learn a lot of theorem about the convergence of the Fourier analysis. If you have some real analysis background, that you may heard about L1 or L2 or whatever function, whatever some property that you can try to prove. You can try to investigate when f has some basic property that f hat will exist. Okay, and there's also inverse Fourier transformation. Then you do exactly the same thing, and you put let's say omega, and you put let's say omega t dt, and then maybe you take to this 1 over 2 pi, and you go this into the results. So this is f of x for t. Okay, so this is the inverse Fourier transformation, and you can prove this by introduce the delta function. And also in the higher mathematics, that this delta function is not a function; it's a distribution. So you can learn a lot of things. If you are interested, I will post my real analysis video list or in my advanced analysis list that you can check out if you want to learn this. But this is just the standard. And also in physics, is that people like to say that you can transform from the space to the momentum. But basically, it's like the same language, so it's the same. Okay, but now, so second perspective that if you know more about the abstract algebra, that you may heard a thing called group representation. Okay, so today I will introduce the connection of this, but I simply say that if somebody give you so if you learn about group representation, somebody give you abelian group, you can consider G hat is all the irreducible representation of G. Okay, so G hat is all the irrep on G. And a theorem called Pontryagin duality is that for a lot of groups, it has this. Okay, so simply speaking, that even G, you can make a transformation for computing, get another function on G hat, and you can also do this. Okay, so you can view this as like abstract Fourier transformation. I will not talk about details, but simply speaking, that your Fourier transformation is you do the R. If somebody give you a real number, which is abelian group, and you do its Fourier transformation, that you get another function which is R. Basically, the R irreducible representation of R is exactly this exponential minus I omega t. So this is like a more abstract version of the Fourier transformation. Yeah. So this is connected to the today I want to talk about is Boolean function. So this is just the introduction. Okay, and by the way, and the Fourier transformation also have the orthogonality, and that kind of orthogonality condition also comes from the character of the shortest orthogonality for column and the row orthogonality for the group representation. So if you are interested in my group representation video, that I also post my own video below. Okay. Don't worry, this is not difficult. Okay, so let me just create some basic of Fourier transformation on, let's say, on Boolean function, right? So let's say this is 0, 1 to n, right? So your function is considered to be this. Okay, so 0, 1 to n is 0, 1 bits with length n. And if you are crazy enough, that you can say this is z to n. Okay, so this is actually a Boolean group. Okay, and it's very natural to consider for every, let's say you take y to be xn. Let's say this is xn, and I can define another function called chi of y of x defined to be minus 1 summation of xi yi from 1 to n. Let's say for every x belongs to chi of n. I hope this definition is understandable, right? So somebody gives you an n-dimensional n-bit vector, and you inner product with another n-bit vector, and you call this as a character function. Okay. Okay. So this character is actually the character of this group representation. So if you take the Z2 representation, then you get two characters. If you take the z to n, which is exactly inner product, so this guy is actually the inner product of, actually the character of irreducible representation of all the z to n. Okay, so number of character is 2 to the n. Okay, so notice a number of character is 2 to n. So it's exactly the same as the cardinality of the chi of n. Okay, which is the same as the group. Okay. So a very stupid calculation is that if you take y1 to not the same as y2, then you can check the inner product. Okay, I haven't defined inner product, but that may define it. So inner product is that 1 over 2n, the chi of y1x, chi of y2x, and you sum over chi. Sum over all the 0, 1 string. Okay, so this is 0x to 0, 1 to n. Minus 1 x y1 plus y2, right? So if y1 do not exist as y2, then you can prove this is 0. Okay, so this is trivial that you should prove by yourself. Basically, you just expand it, and okay, so let me just maybe write down a proof. Okay, so you can write as x, you can write as minus 1, right? xi yi plus y, sorry about this. I guess there's some problem for my computer. Okay, so let's say this is xi yi, right? So sorry, y. Let's write a proof. Don't worry, this is not difficult. So when you try to learn these kind of things, you should try to prove. Okay, so y1 is different from y2, right? So that means that, let's say I can write this y. So there will be some y, so y is non-zero, right? Okay, so whatever term it is, right? There's always for some I, there is some I such that a minus 1 y I x I, and for let's say xi is either 0 or 1. So there will be some I such that yi is 1. So there will be a term which contribution will contribute here become 1, right? So this will be 0. Okay. So when you write in terms of, you get some summation x1, x2 up to xn, right? But there will be I, right? There will be some I term here, and this term will contribute to 0. So you can easily prove it. Okay. Okay, so this tell you what? This tell you that Okay, so let's tell you that this chi1 and chi2, if y is different, then you get 0. If y1 is the same as y2, then you get chi y1, chi y2 inner product will be 1, right? So obviously, so you get 1 2 to n and 2 to n, which is 1. Okay, so right, you get chi1, y1, chi y2 will be delta y1 and y2. So which means that chi forms also normal basis. Okay, of chi of n. Okay, so that means any function. So any function. So let's say somebody give you a function that define on this can be written as a unique expansion, right? So this is trivial that if you learn the linear algebra, because it's also normal basis. So the results will be you can. So this is f of x, right? So you can do f and chi of y, and you do the inner product. And you do chi of y of x and the sum over y. Okay, and this f chi of y inner product is basically, sorry, not integral. It's the summation for f of okay, so as you said, it's f of sorry, it's f of x and the chi of y of x, and I sum over x. Okay, so this is called the f hat of y. Okay, so this is the Fourier transform. This f hat of y with this is a Fourier transformation, and it's inner product, right? So 1 over 2. Okay, so this 1 over 2 to the n, this summation with all the x, such as f of x and x y of chi x put in here. This is the Fourier transformation of the Boolean function f, and then you get this expansion, right? So this is just character, right? So character in this case is just -1 to something, and then if you replace with the exponential minus I omega t, that you get real. So if in terms of group representation, this is a larger framework that you can unify. You can unify it. If you know the group representation, and then you have some background for it, then it should be not difficult. Okay, so this is this, and this is this. Okay, so this is what I just said. This is a Fourier transformation of Boolean function. Okay, so it seems like that we finished. Okay, so let me just write down a formula. So f hat with g defined to be, let's say you sum over, you do the inner product, sum over all the y, take with all bit string, and f has a y, g of y. This theorem is what? This theorem is another. This is possible. Okay. Okay, so possible theorem is the same as when you do the let's recall. So if you do the real, like the physics or the engineer mathematics version, that I think you get the f hat of this transformation, right? If you do square and d omega or 2 pi do integration, should be the same as you do the original integration. Okay, so you can prove this by orthogonality. So proof skip. Okay, because you can view it as exercise. It's not difficult. Okay, but one thing, final thing I want to say is okay, final thing I want to say is the convolution. I think it's interesting. So I think we can spend a final spend a time talking about this convolution results. Okay. So finally, I want to describe this so-called convolution. Okay, so let me recall in the usual usual Fourier analysis, right? You get right. You can prove that when you convolution with g hat, and so okay. So let me just write down. You take two f and g, and then you get the Fourier transformation called f and g hat, and you can easily show that if you times f convolution with g, and then you do the Fourier transform, then it becomes the f times g. Okay, so the product in Fourier, the product of the Fourier function is the same as when you do the convolution and you take the Fourier transform. Okay, so this is the usual one. Okay, so there should be the same thing, right? The same in the Fourier transformation. Okay, so the same. Let's say consider two function from chi of n go to real number. Okay, in this case you can do reals. Okay, yes, let's assume I do reals, and you do f g of x. Right, you define it as a convolution. So this is the Boolean function. So 1 2 to the n f of y g of x plus y. Okay, so it's mod2, right? So when you define in a real variable, then you should define fx minus y g of y dy. Let me just record in a real variable that usually you will define it to be g of x minus y g of y dy. Okay, so this is the real convolution, right? The real version. In this case, I define f of y g of x plus y. This is okay, right? Because I just changed my minus y to y, but we are in the mod2, so it's fine. Okay, sum of y. Okay, so which is all the 0, 1 to n. Okay, so check. So check that if I do this and do the convolution, then I get half f this, right, with x, the chi of y x and x. Okay. So let me just skip this 0, 1 to n. So this is a convolution. I mean, this is the Fourier transformation of the convolution, right? Which is y over 2 to the n summation x and z f x plus z g of z chi of y of x. This is trivial, right? You just write down the definition. Okay. This is trivial. We just write down the definition. Okay, so what we should do? Okay, so what we should do? So what I should do is very trivial, right? I need to prove. I hope to prove these guys actually have this and with this, right? So simply speaking, that let's write chi of yx in terms of, let's say, minus 1x dot with y. As a vector, right? So I can change it into x plus z, right? So I could change it to x plus z with y with another yz, because I'm in mod2, right? So I can do yz will be 1. Okay, so this will be chi of y f x plus z and chi of yz. Okay. So this term will give you y over 2 to the n x and z and fx plus z chi of yx plus z and the g of z chi of yz. Okay, you separate this z with these two and separate this x with these two, and you do a change of variable. Then you say that this x, these three terms will give you f hat. And these three terms, g and chi yz, and this with this z summation z, these three terms will give you g. Okay, maybe let me just write clearly. Let me just do write carefully. I think up to now it's already trivial. So let me just write. So you can write down these terms as 1 over 2n summation x fx plus z chi of y x plus z. You don't care about this z, and then you write 1 over 2n summation x summation z g of z chi y of z. Okay, so this is a g hat. This is f hat. Right? So you get f hat times g hat is the same as f cross f convolution g, and with the transformation. Okay, so we talk about convolution, and we talk about the definition of the Fourier transformation. I think this is enough. So you know what is the definition and then basic idea of the Fourier transformation on the Boolean function. And the next time that we can talk about some, I think this is I think it's just all right, but there are many applications and idea that one can prove using these powerful tools. It's very amazing that you can come up with so many different things. See you guys next videos. Okay, so hope you guys subscribe to my channel.